So we're all setting it up. My name is Scott Crowder. I am the CTO for IBM Systems. So I run technical strategy, transformation. But what I'm here to talk about today is something else that I run, which is commercialization of quantum. So to Bob's question on disruptive, disruptive is definitely in the eye of the beholder. From a hardware point of view, I actually don't see quantum computing as being disruptive to me as an IBM systems provider. I see it as an enabler. Quantum computing is going to augment classical computers. It's going to enable us to do things that we were never able to do before. I mean, there's a whole class of problems out there that Danny was kind of touching on a little bit that are really just very hard to do with classical computing. We tend to sweep them under the rug. You guys tend to spend a lot of time trying to figure out best heuristics to go after them. But they are real problems that if we could find a solution to, would have disruptive impact on society. The first person who comes up with the best algorithm to get, a better financial portfolio optimization, the best person to come up like FedEx with the logistics, the best route from an optimization point of view, the person who can better simulate quantum chemistry, can come up with new materials, better drug discovery, et cetera, et cetera. So from that point of view, quantum computing is disruptive. But from my point of view as a systems provider or a hardware designer, NVMe, solid storage class memory, that driving software-defined storage, to me that is much more disrupting to my business and I think hardware design. And maybe we'll talk about that a little bit more in the panel. But quantum computing. All right, so what is IBM and other people in the industry doing? Danny talked a little bit about D-Wave. D-Wave is one kind of quantum computer. What I'm talking about is a slightly different kind of quantum computer, which is a universal quantum computer. I will try not to have any marketing in here. If I have marketing in here, feel free to raise your hand and throw things at me. So this is early days. If you're familiar on the right versus the left, they look very familiar, right? I mean, I keep telling people that we're really in the 40s in quantum computing, especially from the universal side. But we're at the point now where we're building real systems. IBM has had a system up and running, publicly available on the cloud, nonstop since May of 2016. So we've had a public cloud service that anybody can log into, run on a real quantum system, albeit small one, since last May. But we know how to operate these things. We know how to keep them calibrated on a daily basis. We know how to run them. We know how to keep the coherence times fairly stable over long periods of time, which is the first step you need to do to move into the next step, which is commercialization of the technology. So talk a little bit about universal quantum computers. So this is a nice bridge into the chart that was shown before on terms of what HPC does, what HPA does, and what kind of problems they solve. A quantum computer, a universal quantum computer, is really good at solving, or holds the possibility to be really good at solving these types of problems. Small number of bits in, large probability space, where you're looking at 2 to the n probabilities, small number of problems out. Now the good news is there are a lot of problems like this in the world that are non-polynomial, that are exponential. I won't go into NP complete, NP hard, blah, 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 blah. But what quantum computers hold the promise to do is there are a lot of problems that are NP hard, which may be easy for a quantum system. And those are the problems that it holds a possibility to be good at. We know that in the way foreseeable future, you have something like Shor's algorithm, which is for decryption, that has been proven to be quantum easy. But there are a lot of other problems that we believe will fall into that category as well. So we're very close to this point where we get to the size systems where you have 50 to 100 qubits. This sounds really small, but remember that possible probability space you can grow is 2 to the n. So 2 to the 50 is a larger system state than on the world's largest supercomputer. You can't simulate today a 2 to the 50 quantum computer and all the system state that can solve on the world's largest system. Now I think that number will continue to creep up. It's like it was at 43 and it's at 45. It'll probably creep up to the 50, 60 range, over the next couple of years because people keep working on this. But someplace in the 1500 space, you're going to see a quantum system that can, for a particular type of problem, can be done on a quantum system that you can't practically do on a classical system. When you get to about 1,000 to 5,000 range, then from our point of view, you start talking about production. You start talking about not just being able to run one molecule and simulate one molecule that you can't practically do, but run it on a continuous basis, looking at a lot of different molecules, looking at a lot of different kind of stuff. And then when you get up to 1 million, then you're starting talking about the holy grail, fault tolerant. But this is not in the next decade. Our belief is these two steps are in the next decade. So this technology is real. Right now it's at a state where the real computers that are out there that you get access to are less than 50 qubit size, but IBM, Google, other players are building it, so we will be here within the next few years.